The previous class, we started discussing about the multi-level inverter, space vector modulation scheme for multi-level inverters. So we started with three-level inverter, so especially diode clamped multi-level inverter. Right. So first we obtained the space vectors for the diode clamped multi-level inverters, and we have found that it is 2 to the power of 3 to the power of 3. So that is 27 space vectors you have, right? And there are 3 switching states. So positive switching states, zero switching state, and the negative switching states, right? So positive switching states, you will get E voltage at the inverter terminals. So zero switching states, you will get 0 voltage at the inverter terminals, and for the negative switching states, you will get minus E voltage across A and Z, right? So that is inverter terminals, right? So this is for P switching states. So these upper 2 switches are on, right? So for zero switch states, so only this second device is on, that is S2 is on. For zero switch states, so all upper 2 switches are off, right? So that is the one. So this is the what it is summarized in this table, right? So which device is exactly on, right? So based on this P0N, right, and we have 27 switching states. Okay. So how these switch states are calculated? So here, so by using this same way, how they are two-level inverters. The first thing is we need to transform this into alpha beta transformations. After that alpha beta transformations, we need to substitute the individual values. For example, we have switch states, right? So this is E voltage here. So this is at the same time. So VBZ minus E voltage here, and this is E voltage, right? So based on that, so this is P and this is N, and this will be E. So voltage is, what is the switch state? For example, in this particular case, what is the switch state? So this is positive E, right? So that means switch state is P, and this is at the same time, what is this state? So what is the voltage here? Minus E. So that means it is negative, and at the same time this is positive, right? So the switch state is P and P. Similarly, this switch state is 0 here, so this is also 0, and this will be minus n, right? So this is 0 0 n. So based on that, so we have these equations, or not, no, based on that we have the switch states are developed, right? So out of these 27 space vectors, so we have 3 zero vectors. So we have 3 zero vectors, and their magnitude is equal to 0. So they have P P P 0 0 0 and N N N, right? And remaining 24, so that is divided into 3 categories. So one is the small space vectors, medium space vectors, and large space vectors. Small space vectors that consists of P and 0 or N and 0. In case of medium space vectors, it consists of P, N, and 0, right? And in case of large, so it doesn't contain 0 states, it contains P and N only, right? So this is small, so this is medium, and this is large, right? So these vectors are rotating in space. These vectors are rotating in space, and we have these magnitudes. In case of small vectors, so their magnitude is equal to 0. In case of p-type, in case of small space vectors, as we discussed, so we have p-type small vectors and n-type small vectors. So we have 6 p-type small vectors and 6 n-type small vectors. So 6 p-type small vectors, so this is contains only p and 0, right? So whereas another n-type, so it consists of like this, and its magnitude is 1 by 3 Vd. Its magnitude is 1 by 3 Vd. Similarly, we have this medium vectors. It consists of P0 n, right? It consists of P0 and n. So we have again 6 medium vectors are there, and its magnitude is root 3 by 3 Vd, right? And we have this large vectors, so it is magnitude is 2 by 3 Vd, right? Its magnitude is 2 by 3 Vd. Okay. So in case of two level, so what is the magnitude? So what is the magnitude of space vector? So what is the magnitude of space vector in case of two level? What is the space vector? It is 2 by 3 Vd e to the power of j0 j pi by 3, like that, right? So here if you observe that, so large vector space vector, so that magnitude is also 2 by 3. In case of two level, so that space vector magnitude is also 2 by 3, right? So if you put all these things in the space vector diagrams, we have this alpha axis here and we have this beta axis. So here, so this zero vectors are lies here. Zero vectors are lies in the center. And we, yes. So we have 6 small vectors are there. So actually 12 small vectors are there. So this is V1, V2. Again, we had two types. So one is V1P and V1N. So that is P type small vector and N type small vector. So we have V4, V5, V6, and its magnitude is Vd by 3. All right. So next we have medium vectors starting from V7 to V14 or V7 to V13, V7, V12, right? So V7, V8, V9, V10, V11, and V12. So here it is making 30 degrees angle with respect to the small vectors. It is making 30 degrees angle with respect to the small vectors. And we have large vectors, so which is in phase with the small vectors. So its magnitude is double the small vectors. Its magnitude is double the small vectors. So this length is 2 by 3 Vd. So which is equal to the two level. So which is equal to the two level modulation signal. So magnitude which is equal to 2 by 3. So Vd. So that is also 2 by 3 Vd. Right. Okay. We can inscribe a circle here. So this will be something like this, right? So what is the radius of that particular circle? So what is the radius of that particular circuit? So what is the radius of this circle? So how much this value is? So this radius is root 1 by root 3 Vd, right? So its radius is 1 by root 3 Vd. So remember, if you go back to our previous discussions, when you're discussing the two-level inverter, so what is the radius of that one? So what is the radius of the circle? Somewhere we discussed it, right? So what is the radius? So this is Vd by root 3. So that is its radius, right? In other words, so that is the maximum possible voltage. So that can be, just a second. And that circle radius is that is also equal to 1 by 3 Vd. So in other words, so that is the maximum voltage so one can obtain so without over modulation, right? So that is the maximum voltage one can obtain without over modulation. So that value is equal to Vd by root 3. Right? Its value is equal to Vd by root 3. Okay. So we'll come back to this. So when we define the modulating signal again, right? So this is equal to the medium vector magnitude. That is equal to the medium vector magnitude. Okay. So here, so this is the complete space vector diagram. So again, so this is divided into 6 sectors with a angular speed or with angular displacement of 60 degrees each, right? So here this is sector 1, 2, 3, 4, 5, 6. So we have 6 sectors, right? So here these are centered around here. So this is V1 vectors. Again, there are two possibilities, either P00 or 0NN. So P0P or 0N0. So 0P00P or NN0 likewise. So this is 0P0 and N0N, right? So if you have 0 here, so we have N here. If it is 0 here, we have N here. If you have P here, so we have 0 here. Just complementary of that. just a complementary of that, right? So this is the overall space vector diagram. So it consists of six sectors, right? And if you notice that, so each sector is again divided into four parts, right? So this sector is again divided into four parts. So you have one triangle here, so another triangle, third, four, right? So this is each sector is divided into four regions. Each sector is again divided into four regions, right? So why we are divided into four regions, right? So because so we have some intermediate vectors are there, right? So let us assume that there are, this is the reference one, this is the reference vector, so which is same as the, it will be the same as, so what we discussed for the two level, what we discussed for the two level inverter. Okay, so it is rotating at speed omega, so which is equal to 2 pi f1, that is angular speed, so which is equal to 2 pi f1, right? So here this is rotating, so based on this length, right? So based on length, so we need to choose the nearest vectors. So we need to choose the nearest vectors. So let us assume that this v reference is false here. So this red one is the v reference. So what are the nearest vectors for this v reference? So what are its nearest vectors? What are its nearest vectors? So this v0, right? So this v1 and v2. So these are the nearest vectors, right? Agree? Right. Similarly, so if it is false here, so what are the nearest vectors? It's false here.
V13,
So what are
V14,
the
sir.
nearest vectors?
V13, V14.
This is the one, right? So this is v1 here, so v7 here, and this is v2, right? So this is the magnitude is somewhere located here, right? So these are the nearest space vectors. So v1, okay, v7 and so v2 are the nearest space vectors. Similarly, so if it is here, so what are the nearest space vectors? What are the nearest space vectors? So v1, v13 and v7, right? Agree?
Yes.
Okay. So again, so if it is false in the fourth region of sector 1, so what are the nearest space vectors? So we have v7, v14 and v2. Understood? So each sector is divided into four regions. So depending on that, so it will be, or depending on its location of v reference, so we will select the nearest space vectors. We'll select the nearest space vectors. Understood? So this is for region 1 in this particular case. So this is v2 here, so v14 and v8. So v2, v14, v8. So that means you have one small vector, so one large vector and one medium vector. Yes. Yeah. So this is how we will select the space vectors, right? So how we will select the space vectors? So depending on the magnitude and the angle of the reference vector. So depending on the magnitude and the angle of reference vector. All right. So once it is done, so what we have to do is we need to calculate the timings. So how much time a particular vector is on, right? For example, if it is false here, so how much time this v1 is on, so how much time this v2 is on, so how much time this v7 is on, so that we need to identify. All right. So that is our next job. So let us assume that a simple case, okay, a simple case. So where it is in sector 1, so where it is in sector 1, the reference vector is falls in the region 2 of the sector 1. So region 2 of sector 1. So we have reference here. All right. So let us see. So here this is formed with, so how many, so how, so what are the nearest space vectors here? So V1 here, so V2 here, and V7 here. So what is the value of V1? So what is V1 vector? So what is its value? So 1 by 3 Vd e to the power of j0. So that means 1 e to the power of j0. So this is equal to 1 by 3 Vd only. So what is the, another one? Next space vector. So V2 vector. So it will be 1 by 3 Vd e to the power of j pi by 3. J pi by 3, right? So we have V7 vector. So what is the magnitude of V7 vector? What is the magnitude of V7 vector? 1 by root 3, right? So Vd e to the power of j pi by 6. So this angle is 30 degrees. Understood? So here what we assume that, so this V1 vector is on for T duration of time, and this V2 vector or this V7 vector is on for TB duration of time, and this is on for TC duration of time. So this TA duration of time, TB and TC duration of time, right? So what is the next step? So we need to substitute in the equation, right? So we need to substitute in the equation. So we have this V reference. Okay, so V reference which is equal to V reference vector e to the power of j theta, if this angle is theta, right? Okay, so we have volt second balance. So T A into V1 plus TB into V7 plus TC into V2, which is equal to TS into V reference. So this is what volt second balance is, right? So substitute each one. So substitute each one. So we have this TA into 1 by 3 Vd plus TB into 1 by root 3 Vd e to the power of j pi by 6 plus Tc into 1 by 3 Vd e to the power of j pi by 3, which is equal to Ts into V reference. So that is V reference e to the power of j theta. All right. So we can separate the real and imaginary terms. So we can separate the real and the imaginary terms, right? So we have real terms. So this is TA. So there is no sine term here, right? So there is no sine term here. So e to the power of what is the formula? Cos theta plus j sine theta, right? So there is no cos term here. So this is real terms. TA plus 3 by, so what is e to the power of j pi by 6, so which is equal to root. So what is pi by 6? Sine pi by 6. So what is cos pi by 6? What is cos pi by 6? Just simple thing, we are writing e to the power of j pi by 6 as cos pi by 6 plus j sine pi by 6, right? And we are separating the real and real and imaginary terms. So what is sine pi by 6?
0.5.
0.5 means it is 1 by 2, right? So what you will get if it is 1 by 2? What you will get? 1 by root 3 into 1 by 2. No, what is cos pi by 6? So this is cos pi by 6, right? Real time.
Root 3 by 2.
Root 3 by 2, right?
Therefore,
that
1
means
by 2. 1 by 2
1
VD.
by root 3 into root 3 by
Root
2.
3 by VD.
So what you are getting is 1 by 2.
Yes.
So 1 by 2 TB plus TC into, so how much it is? Cos pi by 3. So what is cos pi by 3? 1 by 2. 1 by 2, right? So that means 1 by 6 TC okay. This is all with VD, right? No. Something we are doing it wrong.
Sir,
So we have 1 by
into
VD
1 by 3.
into,
So, TA into 1 by
or
3.
else we can separate this 1 by 3 VD term, right? 1 by 3 if we separate this one, right? So just it will be, I think 3 by 2 here, and this will be 1 by 2. So just check it out. So now this is correct. I'm just separated 1 by 3 VD. Just check it out.
Yes.
I just separated 1 by 3 into VD term. So which is equal to, so what is this value here?
TS.
So what is this value? TS V reference cos theta. Agree?
Yes.
TS V reference cos theta. Similarly, the imaginary terms. So we have some imaginary terms, right? If you do that, so what you will get here? Similarly, we can, in the same way, we can subtract the 1 by 3 VD term here, which is equal to TS V reference sine theta. So what is the first term? So first term is 1. No, first term is
0.
sine 0, right? So it will be 0 plus TB. What is TB here? So that is sine pi by 6, that is 1 by 2. 1 by 2 is already 1 by 3 he is there, right? So that means root 3 by 2 TB plus, so what is TC here? So TC is sine pi by 3. So that is root 3 by 2. So root 3 by 2, yeah, root 3 by 2 into TC. Just check this. Just check it out. So we have separated the real and imaginary terms. It's separated, so the real and imaginary terms, right? Okay. So we can solve this one. So along with that other equation, TS equal to TA plus TB plus TC. Right. So if you are doing so, so it will be something like this. So TA equal to, so it will be TS into 1 minus, right? So 1 means 2 root 3, 2 root 3, V reference by VD, okay, into sine theta. Similarly, TB, right? So TB is TS into 1 minus, not 1 minus, 2 into root 3 V reference by VD, okay, sine pi by 3 plus theta minus 1. Similarly, TC, okay, CTC, so which is equal to TA minus TS minus TA minus TB. So that can be done as TS. So this is for sector 1, right? This is for sector 1 and region 2. Understood? So this entire thing is valid only for sector 1 and region 2. Similarly, for every region in sector 1, so we need to calculate. So similarly, for every region in sector 1, so we need to calculate, right? Understood? So now the thing is that, so how to identify, so whether V reference is false in which region? So that is one of the step, right? So V reference is false in, so which region? So how to identify that? So how to identify, so whether it is in region 1, 2, or this, for example, this is the case, right? So how exactly you are identified whether it is in region 2? So what we have to do is we need to write a program or by using some simple trigonometry techniques, right? So for example, so you know that theta equal to 15 degrees. Okay? Theta equal to 15 degrees. So we have some value of V reference is there, right? If this is 15 degrees, right? So where exactly it is false? So 15 degrees, this entire thing is 60 degrees, right? This entire thing is 60 degrees. So 15 degrees, this is 30 degrees. So therefore this is 30 degrees. So 15 degrees is false somewhere here. Okay. So that means the thing is that either it will be in region 1, 2 or 3. It will be region 1, it will be in region 2 or it will be in region 3. So definitely it is not in the region 4. So based on that angle and based on the magnitude, again the magnitude we need to calculate. So based on that magnitude, so we need to identify, so whether it is in sector 1 or whether it is in region 1 or region 2. So we need to find these intersecting points, right? Where exactly it is intersecting that. So based on that length of that, based on the length of V reference vector, so we need to identify the region. So for that, we need to write some simple algorithms. We need to write simple algorithms to identify the region. Understood? For example, it is false in 45 degrees, right? This is 45 degrees angle. So definitely it is not in region 3. It may be in region 1, maybe in region 2 or region 4. So next thing is we need to identify where exactly it is intersecting, right? So if it is intersecting beyond that point, right? So what is now that it is in region 4, right? Here also we need to identify this intersecting point here. So we have two intersecting points, right? So this is one intersecting point here. This is another intersecting point, right? If the length of the vector is less than this intersecting point value, so that means it is in region 1. If it is in between this two intersecting points, so that is in region 2, and it is higher than that intersecting points of both, so that means it is in region 4, right? Yeah. So next thing is, so how to obtain these intersecting points? So how to obtain these intersecting points? You know this angle, right? And this point, and you know this point, so we can find out the straight line, so that is going, right? So we can represent this line, and we can also represent this line, right? So that we can find out the intersecting points. So that we can find the intersecting points. Consider this is in xy plane. So based on that, so we have some point here, right? So it will be, what is it, x-axis somewhere here and y-axis somewhere here. Similarly, this is x-axis somewhere here and y-axis somewhere here. So we can represent this line. So we can represent this straight line. So based on that, so we can write the equations of the straight line equations. From that, we can find out the intersecting points. So a lot of algorithms are there to obtain these intersecting points. So once it is done, so for every sector, right, in every sector, in every region, so we need to calculate this TA, TS, TA, TB, and TC. So once this is done, so there is another one. So that means we need to define the modulation index. So we need to define the modulation index. Right. So as we observed that, so this is peak value, or this value is equal to 2-level inverter value. So whatever the modulation technique or whatever the modulation index definition, so the same definition we can use here. So in the previous class, so MA is defined as, if you remember, so how we defined MA? So this is MA is defined as root 3 V reference by VD. So root 3 V reference by VD. So we can also use the same thing. So root 3 VD by V reference. Okay. So root 3 VD by V reference. So root 3 V reference by VD. So this is root 3 VD by V reference actually. Okay. Root 3 V reference by, yeah, this is correct only. Root 3 V reference by VD. Yeah, root 3 V reference by VD, right? So what is the maximum reference value? So without over or without encroach or without what is the maximum one? So this is the one, right? So what is its value? What is the V reference value? So what is the maximum V reference value? So which is equal to 1 by root 3 VD. Remember that, right? So this is equal to medium voltage vector, so which is equal to 3 by root 3 VD. So that is equal to 1 by 3 VD. So this is the maximum voltage so one can generate, or the V reference maximum. So which is equal to 1 by root 3 VD. Understood? So now MA, so which is root 3, that means corresponding to maximum voltage we are calculating. So V3, it will be root 3 VD, right, by VD. So which is equal to 1. So MA equal to 1. So that means so maximum voltage can be obtained. So maximum voltage can be obtained. So corresponding V reference is equal to VD by root 3. Right. So meaning is, right. So meaning is from here to here, this is 0 MA, and this is corresponding to MA equal to 1. Understand? So this is how we will define the modulation index. For example, if you have half of the voltage here, right? So that means we need to operate with MA equal to 1, right? So that means it is root 3 VD. So MA equal to 1 means root 3 VD into 0.5. So it will be, so VD by 2 root 3. So with the length of the reference vector is VD by 2 root 3. So that means it is operating at 0.5 modulation index. In other words, half of the voltage, half of the maximum voltage in the linear range. So that can be obtained. Okay. So once this is done, right? So once this is done, so we need to calculate, this is for sector 1, right? So this is if you substitute here, so in place of root 3 V reference, right? So in place of this root 3 V reference is there, right? So in place of this root 3 V reference, so we can substitute the value of MA. So we can substitute the value of MA, modulation index. Right. So once this is done, so we need to calculate the dwell times for every sector and every region. So we have region 1, 2, 3, 4. So we have 4 regions are there. So in region 1, so this is composed of V1 vector, V0 vector, and V2 vector. In region 2, so we have this V1 vector, V7 and V2. So these are the nearest vectors. So again, V1 vector, V7 and V13 vectors. So this is V14, V7 and so V12. So these are the nearest vectors in each region. Okay. So based on that, we need to calculate this TA, TB and TC times. So we need to calculate this TA, TB and TC times. All right. So up to this, the procedure is same, right? So irrespective of what method you're using, right? The space vector modulation means, so up to this, so this procedure is same. So what is the next step? So once you obtain this TA, TB, TC values, so we need to generate a switching pattern. So we need to generate a switching pattern so that the switching losses will be minimized. So that the switching losses will be minimized. Right. So in case of this 3-level diode clamped inverter, so there is another one, right? So there is another one, so that we'll study. So there is another demand. So when we arranging the switching pattern, so based on this TA, TB and TC, right? So that is, we can minimize the neutral point voltage. So we can minimize the neutral point voltage. Okay. So we can minimize the neutral point voltage, right? So here, so unlike 2-level inverters, so 2-level inverters on the DC side, sometimes we'll connect a capacitors, right? So that objective of that capacitor, for example, if you have 2-level inverter, okay, so we have, so this DC source is there. So we have inverter is there, right? So across this one, we normally connect a capacitor. So the objective of this capacitor is to reduce the or to eliminate the ripples that contains in the DC source. If at all the DC source is not a pure DC, right? So it is containing some voltage ripples. So that can be taken care by this capacitor. And there is no load current, so that is flowing in through this capacitor. So the capacitor, so there is no load current, so that is flowing through this capacitor. So usually the size of this capacitor usually small. The size of this capacitor, so usually it's small, because there is no load current that is flowing through the capacitor in case of 2-level inverters. But whereas here, right? So whereas here the midpoint is formed by splitting the two capacitors or splitting the two DC sources. Right. So therefore, definitely, so we need to access the midpoint to create some extra, extra level or extra voltage level, right? Positive voltage, 0 voltage, and this, right? Extra level. So therefore, what we have to do, what the reason is, what the consequence is, so there will be some current flow in the neutral point. So there will be current flow in the neutral point depending on the operation, right? So depending on the operation. So we have two types of operations. So one, assume that this is source here and this is load. Assume this load is a motor. So the power flow will be like this. In case it is a motor, if it is operating as a generator, so the power flow will be like this. And the current flow will be like this, right? So there are some chances, right? So there are some chances. So let us assume that so it is operating as a motor. So it is operating as a motor. So if it is operating as a motor, so what is the direction? So if it's a motoring mode, so that means the current or the power is flowing from source to load. So this is source and these are the source, right? So let us assume that, so this is the direction of current. So this is the direction of current. So how exactly, so we can represent this one. So let us assume that this is 3-phase load. Right. So this is A phase terminal and this is B phase, C phase terminal, and this one is the B phase terminal. So we have load here, this capacitor is splitted here. Right. So this capacitor is splitted here. So let us assume that, so this is connected to A phase, the upper portion is connected to A phase, and assume that this is the direction of current. If this S1 and S2 are on, right? If S1 and S2 are on, so obviously it will be connected to A phase, right? So we need to provide the written path, right? So we need to provide the written path. So which is provided from B phase and C phase. So there is a lot of chances, right? So one is something like this. So this is one scenario. So where this is the written current will flow. Agree? So this is one case. So another case, right? So another case, it is connected to the midpoint and it is connected like this. Agree? So this is second case. And the third case, so it will be something like this. Some portion of the current is written through B phase and some portion of the current is written to C phase, right? So what exact the situation is, so that all depending on their instantaneous voltages. That all depends on the instantaneous voltages, right? So here, for example, if you have one case, so we'll talk about these cases later. So this is the case. So both B phase and C phase are connected to the 0 voltage. So A phase is connected to, right, A phase is connected to the positive voltage and B phase and C phase are generating 0 voltage. So what is the switch state here? So A phase P, right? So this is P, right? So here N here. So this is 0. So this is P 0 0. This is the switch state, right? So now, right. So there are two options. So this circuit is closed here. So we have this DC source, right? This is VD. So this is VD. So this current is flowing like this. The upper one is providing the one, right? So here the thing is that, so here this current, so where this current will go, so this will go through this capacitor, right? Agree? So this current will go through this capacitor. Understood? If you notice that, so the top capacitor, the current is going away, and in the bottom capacitor, the current is going towards the capacitor, right? So what is it is charging or discharging? There is simple thing, right? So you have a capacitor is here. The current is out of the capacitor. Assume this current is positive, right? So whether this capacitor is charging or discharging, so this capacitor is charging or discharging? Simple question.
Discharge.
Discharging, right? If it is a battery, so we are feeding this battery to some other source, so it is in discharging. So whereas in the bottom capacitor, so the current is inside, right? So which is charging this positive, same positive current from this point of view, right? The current is going inside that, right, capacitor. So what is the fate of this capacitor? It is charging or discharging?
Charging.
So it is charging, right? Agree? So one capacitor is discharging and other capacitor is charging. Understood? So one capacitor is discharging and the other capacitor is charging. So let us assume that this is started with 400 volts, right? So that means it will be 200 volts and it is 200 volts, right? Initially. So by this operation, right? So by this operation, what will happen? So this voltage is reduced to 190 volts, right? See, both sum should supposed to be 400 volts, right? That means this voltage is how much it will be increased to 210 volts. So because there is some flow in the neutral point, and so that is right. So that is deviating the charge and discharging of these two capacitors. So therefore the voltage across the capacitors are varying. So now it is 210, 220 volts. So earlier one is discharging, that voltage is reduced, right? And another one is that is increased. So now what will happen if the waveform, for example, the waveform is generated VAZ. So how it will be? So for example, this positive off cycle, so its voltage is now it is 910 volts, and then the negative off cycle, so its value is 210 volts, right? Agree? So positive voltage will be generated by the upper capacitor and the negative voltage generated by the lower capacitor. So now it is 190 volts and it will be 210 volts. So that means there is definitely some DC offset. So that means there is definitely these two capacitors are not balanced. Understood? These two capacitors are not balanced. Clear? So that means what you understand that, right? So whenever, if it is something like this, right? So this is one scenario we're talking about, right? For example, this is the written path. This is for B phase. This is the written path for both phases. So this is B phase written path and C phase written path. So now tell me, is there any change in the capacitor voltage? Is there any change in the capacitor voltages? Is there any change in the capacitor voltages? So for example, this is 400 volts, right? So what is the value here? So this must be 200 volts and this must be 200 volts, right? So there is no change in the capacitor voltages because there is no current that is flowing through the capacitors. Understood? Clear? Okay, right. So that means what you understood that, so whenever there is a current flow inside the neutral point, so definitely, so it will deviate the capacitor voltages. So definitely it will deviate the capacitor voltages. So this particular problem is known as neutral point voltage deviation. So this particular problem is known as neutral point voltage deviation. So this is especially occur in diode clamped multi-level inverters, right? So with this, right? So with this, the neutral point is varied, or in other words, these two capacitors will become unbalanced, right? It's supposed to be 200, 200 in ideal case. Right? So there will be some deviation in this capacitor voltages. So this should be minimized. So usually the voltage between this one and this one, so this Z and this negative, so this VAZ, so this VAZ, in other words, simply VZ, so this is known as neutral point voltage. So this is known as, so usually known as neutral point voltage. Understood? Right. So somehow we need to minimize this one or minimize the neutral point voltage. So by using the space vector modulation technique, so we can minimize this neutral point voltage by appropriately switching the switching instance, right? So even though we are using, or even though still this problem is existed, so after that what we had to, still we cannot solve this problem permanently. So we can connect some external hardware circuits. That means the two quadrant choppers, we can connect that, so to reduce the neutral point voltage. So how exactly that can be possible, so that we'll discuss in the later classes. So, understood, right? So this is about the neutral point voltage problem. So this problem is particularly evident in 3-level inverters or neutral point inverters. So that's why if you're going for higher levels, for example, if you go for 4 levels, 5 levels, and so on, the thing is that, so we cannot balance all the 4 capacitors. So for example, if you have 5-level case, So we have 4 DC sources are there, right? So you have one neutral point here, so here, right? So every time the current flows here and current flows go there, right? So that means there is a current flow in all the 3 neutral points. So it is formed, for example, X, Y, Z, right? So there will be a current flow in X, Y, Z. So that is deviating the capacitor voltages. So that thing is deviating the capacitor voltages. So now it is no longer equal or no longer balanced. Okay. So when it is not balanced, the waveform quality will be disturbed. So that means it is causing DC offset. First thing, it is causing DC offset. So when it is causing DC offset, for example, if it is feeding to a transformer, right, if you have DC offset, the transformer core gets saturated and the magnetizing current will be increased. For example, we are feeding to induction machine, right? So induction machine for generating the no load losses or to generate the magnetic flux, some magnetizing current is supposed to drawn. If the voltage consists of some DC quantity, so that means DC will saturate the core of the starter. So if the core is saturated, you need to give the excess current, or it will draw the excess current, so that will substantially increase the no load losses of the machine, whether it's a transformer or whether it is a motor, so that no load losses will be increased. All right. So we need to avoid this one, or we need to minimize this as much as possible. So this is somewhat acceptable. You cannot never maintain these two are equal. For example, this is the case. It may be in 198 volts, or it may be 202 volts, or 199 volts, or 201 volts. So that thing is acceptable. But the large deviation in the neutral voltages, so that is not acceptable. So in next class, so how to improve or how to So how to improve this neutral point voltage by using the space vector modulation technique. So that we'll discuss in the next class. So you have any doubts in today's class? So any questions? If you have no questions, I will stop here.